to have Professor Kannan Soundararajan with us. And I'm really thankful to him for agreeing immediately. In fact, as soon as I sent the invitation, the first response came from Professor Soundararajan. So Professor Soundararajan is a professor at Stanford University, and he's a number theorist, primarily analytic number theorist, but he has contributed hugely in the areas of automorphic L functions, in multiplicative number theory. In fact, his works in moments of zeta function, unique ergodicity problem is kind of pivotal in that area. And so let me list, he's a very decorated mathematician in the sense that lots of awards and recognitions that he has already achieved. He has been given, so I list a couple of them. So he was awarded Salim Prize in 2003 for his excellent contribution in the areas of Dirichlet L functions. He was awarded this Sastra Ramanujan Prize, which is a very prestigious award in 2005, Infosys Science Foundation Prize in 2011, Ostrowski Prize in 2011, and he's also a fellow of the American Mathematical Society. Professor Kannan Soundararajan.
Thank you very much. It's a pleasure to give this talk. I wish the circumstances were better and we could meet in person, but it's also been kind of interesting to see all the activities that are going on remotely. And it is nice to have this opportunity to give a talk at KSOM. So I mainly work in analytic number theory, so there's a little bit of a departure for me. It's a problem involving combinatorial representation theory, something about the characters of the symmetric group Sn. But you will see that the main input in resolving this problem comes from understanding random partitions, which leads to problems which are closer to analytic number theory. What I'm going to speak on today is joint work with a former student of mine, Sarah Palouse, whom you can see here. She's currently at Princeton, and she's a very accomplished mathematician, and you will probably hear her name very much in the future as well. So let me set the problem. So we are interested in the symmetric group Sn. So it's a big group with n factorial elements. And we are interested in the irreducible representations of this group, and in particular in the characters associated to each irreducible representation. So now the irreducible representations for Sn, the number of these irreducible representations is the same as the number of conjugacy classes of the group Sn. And the number of conjugacy classes of Sn is a famous object in number theory. It just counts the number of ways of writing n as a sum of integers. So this is the number of partitions of n. So this is Ramanujan's birthday, not here for me yet, but I guess for you it's already December 22nd. So one of the most famous contributions of Ramanujan has to do with his work with Hardy on the asymptotics for the number of partitions. And we know that there are lots of partitions of n, like exponential of this constant 2 pi over root 6 times square root of n. And then, but not so many as the number of elements in the symmetric group, which is n factorial, but certainly lots and lots of partitions of n, much more than any power of n. Now, every partition of n corresponds by the cycle decomposition of a permutation to a conjugacy class in the symmetric group. And as I said, every partition also corresponds to an irreducible character of the symmetric group. And what we are interested in is if you take a partition lambda, we think of the irreducible representation associated with that partition lambda, and evaluate the character associated to that irreducible representation, that's chi lambda. And we take this character and we are interested in understanding what happens when you evaluate that character at a random element random conjugacy class of the symmetric group. So that's another partition mu of n. So the character table of the symmetric group is a square table. It's a Pn by Pn square table. So where Pn is the number of partitions, and we are interested in the values that you get in this square table. So that's a very classical object, but somehow the idea of how these numbers actually look like, really there seems to have been a numerical experiment done on them very recently within the last few years by Alex Miller. And what he noticed was that these entries in the character table, which are known to be integers, they tend to be even quite a lot of the times. So he computed, so it's not easy to tabulate all of them, because even if you take n, which is only some small number like 76, there are already something like 9 million partitions. So the square table that you're looking at is a 9 million by 9 million square table. But he found that among all these entries, there's a large proportion of them, about 87% of them, happen to be even, and you're only odd like 12% of the time. Okay. Miller also computed what happens if you look at whether these entries in the character table are multiples of 3 or 4 or other primes or prime powers. And again, he found that there seemed to be a preponderance of them, which are multiples of any given prime or prime power. So the data is a little less striking for other primes besides 2. So for n is 38, there are about 26,000 partitions. And then he found that the proportion of even ones is a little bit smaller than what we saw for 76. It's about 82% of the time. So it's gone up from 82% to 87% when you go from 38 to 76. But then there's also like 63% of the time you get multiples of 4, 67% of the time you get multiples of 3, and so on. So 47% of the time you get a multiple of 9. And even if you look at values that are just 0, which are multiples of all of these numbers, there is a large proportion of the time, 36% of the time, you get zeros in this character table. So the question is, what's going on here? Do these fractions converge to some limit as n gets larger and larger? And if so, what are these limits? So based on this numerical data, Miller conjectured that at least if you look at the even values in the character table, he conjectured that most of the values are even. So the probability that if you pick a random element in the character table, the probability that it's even goes to 1 as the size of the table goes to infinity, as n goes to infinity. So if you choose lambda to be any partition of n and mu to be any partition of n, and you count the number of times the character value chi lambda of mu is even, then that's asymptotically the total number of elements in the table, which is p of n squared. Okay? And he made the same conjecture for any other prime as well, that if you fix a prime p and you let n go to infinity, then most of the values in the character table are going to be multiples of p. So p could be any prime that you choose at all. And you might wonder that maybe the same result is also true for prime powers, but Miller seems to have conjectured just for primes. But I imagine that one might think that there are also multiples of prime squares, prime cubes, and so on, with probabilities going to 1. So there have been kind of partial results in this direction. One is a nice result of Miller, which I kind of explained to you why this is true later on in the talk. He showed that if you take a random character, so if you pick a random partition lambda, and you evaluate it at a random element of the group, so G is a random element of the symmetric group Sn, then the probability that that the character value of this element G, that with probability 1, that value is equal to 0. So here, Pn is a number of ways of choosing lambda, and n factorial is a number of ways of choosing G, because we're just choosing elements from the group rather than choosing conjugacy classes. So this is something in the direction of his conjecture, but it's a little bit more crude than the conjecture itself. And the reason for it is that if you look at the conjugacy classes of the symmetric group, they vary dramatically in size. There could be, say, transpositions, which would have a very small conjugacy class, only about n squared elements. And then you could have like an n cycle, which would have and the conjugacy class would be of size n minus 1 factorial. So there's a great variation in the size of these conjugacy classes, and that's not being detected when you just evaluate the character values on group elements. All the values for G in the same conjugacy class will of course be the same, but you're counting the same zero that you get many times in this result. Now, apart from this, there were some special cases in which we knew some version of this conjecture. So if you fix some particularly nice partition mu, so this would be the partition 1 plus 1 plus 1 plus 1 n times. So for this partition, you're just evaluating the degree of the representation attached to lambda. And already in the 70s, this was known by John Mackay. He knew that that most of the values that you compute of the degrees of the irreducible representations, almost all of them are even. And MacDonald had also shown that if P is fixed and N is large, then most of these, or you can actually get a formula for how many of these are multiples of P. And then apart from these, there have been some recent partial results motivated by Miller's conjecture by Gluck and Moratti. And these are all using ideas that Miller himself had in his paper, and I'll review some of these in this talk as well. We also build very much on Miller's ideas towards this problem. And what they had shown was that for certain kinds of columns in the character table, most of the entries in certain columns would be 0 mod P, would be even or even. So Gluck looked at 0 mod 2, but then Moratti also did 0 mod P for any prime P. And some other results, I think, developed independently of Miller's conjecture by Ganguly, Amritanshu Prasad, and Spallone. So what I want to explain a little bit today is a theorem that Sarah Palouse and I proved recently, a couple of months back, that Miller's conjecture is true for every prime P, that if you look at the number of elements in the character table that are multiples of P, it is almost all the entries in the character table. And moreover, you can make it uniform a bit. You can take P to be any prime going up to about log n. So going up to log n divided by log n squared. And in fact, every element in the character table, almost every element, is going to be a multiple of all the product of all the primes up to this point. Okay. So this builds on several of the older ideas, but most importantly, it builds on results that Sarah Palouse had just recently established, where she proved Miller's conjecture for 2, 3, 5, 7, 11, and 13. And then her method seemed to break down at 13. And then what we have done here is to say that actually it works for every prime at all. So the method that I will describe today really uses primes crucially, and it doesn't tell you anything about divisibility of these character values by prime powers. So for prime squares or prime cubes, you'd have to develop something new. And also, if we look at how many zeros there are in the character table, this seems quite unclear at all. I mean, so I will explain that one can show that there's about a constant over log n proportion of zeros in the character table, but that still goes to 0 as n goes to infinity. And it's not clear to me whether the proportion of zeros in the character table should be an actual constant bounded away from 0, or if it just tends to 0. If n is something like 38 or 40, 1 over log n is not going to be distinguishable from a constant. So the fact that we have 30% of or 35% of the zeros in the ranges that we calculate does not really tell us whether that's really a robust proportion or not. So let me try to explain what these character values are and what are some of the ideas that go into this proof. There are kind of a couple of different ways of computing these character values, and we'll kind of need both of them. One is called the Murugannakayama rule, and the other is a formula which goes back to Frobenius. So let me start with the Murugannakayama rule and then try to tell you what that means in terms of producing zeros in the character table. And then we will combine it with the Frobenius formula, which will then give information about finding divisibility by primes p. So the Murugannakayama rule is a recursive way of computing the character value of a character lambda at a partition mu, at a conjugacy class mu. And the idea is that you have two partitions. You have a partition lambda and a partition mu. And the partitions we're going to describe in terms of these diagrams. So this will be a partition of 4 plus 3 plus 2. And then this will be a partition 3 plus 3 plus 3. And both are partitions of 9. And the Murugannakayama rule takes apart from this partition mu. So here all the parts are the same. In general, of course, it need not be. And it gives you a recursive way in which you take one part from mu and you remove it from mu. And if you remove certain other things from lambda, and then you compute the character value of chi lambda of mu in terms of these smaller partitions that you have. So it gives you a recursive way of computing character values in terms of character values for smaller groups. And so if you keep iterating this, eventually you'll be able to evaluate the character value. Okay, so how is this done? If you take a partition, in this example, if you take this partition mu, there's like one part of length 3, and I want to remove a part of length 3 from lambda. And what I should do, what I'm removing are supposed to be rim hooks, which are also called ribbons or border strips. So these are partitions at the edge. So like this partition of 3 would be a rim hook, or this partition of 3 would be these 3 parts would be a rim hook, and then you would be allowed to remove them. So the strips that I'm removing are all strips at the border. So they might be strips like this. They should not contain a 2 by 2 square. So that would not be a border because it contains this 2 by 2 square, but you should just move along the edges. So anything that you get by moving along the edges is called a border strip. And the recursive rule is to remove a partition from mu by removing the allowable border strips of the same length from lambda. So here I have a partition of length 3, a part of length 3, and there are 2 border strips of length 3, so this one and that one. So if I remove those two, I get 2 partitions for lambda, so this guy and that guy. And the Murugannakayama rule says that if I want to compute chi lambda of mu, I compute chi of this guy with a 3 by 3, 3 plus 3 partition, and then this guy with a 3 plus 3 partition. And then by computing those character values, I can determine what chi lambda of mu is. So let me give you one more example to see what's involved here. So if I have a partition, a useful object is called the hook length of a partition of a part. And the hook length of a box is the number of parts to the right plus the number of parts below plus 1 for the box itself. So in this box, I've written 10 because there are 5 parts to the right, 5 parts below, 4 parts below, and then 1 part here. So that's 10. So now, if suppose I gave you some other partition of lambda, say, let's say it's a partition that had a part of length 7 in it, you could ask, well, what would be a border strip that you could remove with length 7? That actually can be answered by just looking for a hook length of length 7. So that's a hook length of length 7. And then the border strip of length 7 would be just to go along the border and find 7 squares like so. Okay, so every hook length corresponds to a border strip of the given length that we have, which also means that if I don't have a hook length, so for example, 11 is not a hook length, and if I gave you a partition of 19 which had an 11 in it, then there would be no border strip that I could find in this partition of length 11, and therefore the Murugannakayama rule would be an empty recursion which means that the character value, if I took this partition of 19 and then I gave you mu to be a partition that contained the part 11, then chi lambda of mu would be 0. Or to state it more generally, if there is no hook length in a partition of length t, then there can be no rim hook of length t. And if your partition mu now has a part of length t, then chi lambda of mu would be 0. So partitions that have no hook length of size t are called t-cores. So what we are saying is that if lambda is a t-core and mu has a partition of length t, has a part of length t, then chi lambda of mu is 0. So this gives you a way of getting hold of lots of zeros in the character table. But to understand that, you need to know something about, well, at what stage can I say that something is likely to be a t-core? And when can I say that a partition mu is likely to have a part t? Okay. So people have studied quite a few properties of the number of t-core partitions of n. So this has a nice generating function closely related to the generating function of all partitions. So for all partitions, it would just be the product of 1 over 1 minus q to the n. And the number of t-cores is a very similar product, but also multiplied by this extra factor 1 minus q to the tn raised to the t. So one beautiful result on t-cores is a result of Granville and Ono, maybe 25 years back now. They showed that if t is any number at least 4, then there's always a t-core partition of n. But we are interested in a slightly different problem. We want to look at a value of t for which maybe almost all partitions are likely to be t-core. So now you might imagine that if t is very large, let's say even if t is close to n, then it's going to be very unlikely that you will find a hook length which is very large as well. So the problem that we ask is how large should t be so that I can guarantee that most of the partitions of n will be t-cores. Okay. So this kind of result is when you fix t, so to speak, a small number like 4 or 5, but here we are allowing t to be large in comparison with n. And this is a reasonably easy calculation based on the Hardy-Ramanujan asymptotic formula for the number of partitions. One way in which you can prove the Hardy-Ramanujan formula, this is the original idea of Hardy and Ramanujan, is to use Cauchy's formula to understand Pn from its generating function, and then to choose the value of the circle on which you integrate carefully. And the idea is to choose the radius of the circle so as to minimize this generating function for a real value of r. And then once you choose the circle on which this value is minimized, there is a method of stationary phase that you could use to understand the leading order asymptotics as well, at least. But Hardy and Ramanujan, of course, did much more, and they uncovered an asymptotic expansion, which is much more accurate. But just to say crudely what's going on, if you do a little bit of calculus with this generating function, the minimum value is attained for this value of r. So it's pretty close to 1 on the scale of 1 over root n from 1. And if you evaluate the generating function at this point, you get pretty close to the Hardy-Ramanujan asymptotic formula. Now, if we are studying t-cores, the rough heuristic idea would be that if you take this value of r that's suggested by the Hardy-Ramanujan formula, then the way in which the t-cores differ from the generating function for all partitions is in this extra factor. If this factor is very close to 1, then you might expect that all the partitions that you're getting, the t-cores are basically the same as all the partitions of n. So this now, with this value of q, as in the formula, this is a simple calculus computation to figure out how large should you make t in order to make this product be very close to 1? You basically want e to the minus t times q to the tn to be close to 1. So basically, you want t times q to the t to be close to 0. So if you just solve for that with this choice for q, then what we find is that if t is larger than basically square root of 6n over pi times log of square root of 6n over pi, plus this extra little bit of log, if it is larger than this quantity, then it's very likely that almost every partition that you have will be a t-core. Okay. So what does this mean? To understand what this is telling you, we should then examine, if I take a random partition, what would be the largest part that it has? If it has the largest part, which is much larger than this, then I would be very happy, because I would then be able to say by the Murugannakayama rule that if you pick a random partition mu, then it's likely to have a part larger than this, and then it's likely that for every mu, for every such mu, almost every lambda will be a t-core, and then we would be done. We would know that most of the values in the character table are in fact 0. That's not quite what happens. People have studied what the largest part of a partition looks like, and I'll explain to you how we barely fail to get a part of the size that we need. But let me say that this all implies already the result of Miller that I mentioned, that if you pick a part G, an element G at random from the symmetric group, then in fact chi lambda of G is 0 most of the time. Okay. So the corollary is just telling you what I explained in words, that if you have a partition mu which has a large part larger than this, then it's very likely that almost all partitions lambda are going to be t-cores, and then chi lambda of mu would be 0. And now I want to say that if you pick a random element in the character in the symmetric group, then that's likely to have a very large cycle in its cycle decomposition. So the element G lies in a conjugacy class, and the conjugacy class is determined by the cycle decomposition of the element G. And if you take a random partition, a random element in the symmetric group, the cycle decomposition of a random permutation is very much the same, and this is something that analytic number theorists would be more familiar with. A cycle decomposition of a random permutation behaves a lot like the prime factorization of a random number. So a random number is very likely to have a prime factor which is larger than, say, square root of n. It in fact has like a 70% chance of having having a prime factor larger than square root of n. And similarly, a random permutation is also likely to have a 70% chance, so log 2 chance of having a prime factor which is larger than, having a cycle that's larger than half the size of n. So what I want to say is that if you pick an element of the symmetric group at random, it's likely to have a cycle which is larger than, say, n over 100. It's very, very likely to have a cycle of length more than n over 100. Certainly with probability 1, it will have a cycle of length bigger than n over log n. And therefore, almost this t will be larger than n over log n, which is much bigger than the square root of n. And therefore, for almost every element in the group, for almost every lambda, chi lambda of G would be 0. Okay, so this is Miller's result, that if you pick a random element of the group, then chi lambda of G is almost surely going to be 0. However, if you look at a random partition, that doesn't look like a random permutation. And here there's a result of Erdős and Lehner, which says that the number of partitions of n with the largest part bigger than, again, the same funny constant square root of 6n over pi, log of square root of 6n over pi, plus something that's just a constant. So something which you could imagine gets maybe is some number going between -10 and 10, let's say. You can compute the frequency with which that happens. And that happens with a certain probability, e to the minus e to the minus e to the minus e to the minus v. Okay, so in particular, if you just ask set v equal to 0, if you ask what's the chance that that all the parts are smaller than root 6n over pi times log of root 6n over pi, then that's about 1 over e. Okay. Again, this is not a hard calculation to make. It's basically working with the Hardy-Ramanujan asymptotic formula and then computing if you break off at whatever point that you're given here, and you understand what the tails of the product in the generating function for partitions looks like, that will evaluate to this probability that we have here. Okay, so what I want you to observe is that this Erdős-Lehner result is very close to the threshold that we want to guarantee that that if T is a little bit larger than this, then almost every partition would be a T core. But it falls just a little bit below the threshold that we need to get almost all partitions being T cores. Okay, so the threshold for getting all T cores was that this is what we had from the Erdős-Lehner theorem, plus a small amount which is going off to infinity, which we don't have here in the Erdős-Lehner theorem. Okay. So we barely failed to show that that a positive proportion of the elements in the character table are 0, and maybe it's not true. So we shouldn't be surprised that we haven't shown that, but it'll at least show you that there is a proportion of like some constant over log n zeros in the character table. Okay, so far I've been just telling you about whether the character values are 0 or not, but the theorem that I wanted to describe was not about whether the character values are 0, but rather about whether the character values are multiples of p or not. So, and I haven't discussed anything about divisibility, so that's the next thing that I'm going to do, and this depends upon the second way of understanding character values, which is through the formula of Frobenius. So there's a different way of computing these character values. So, and which I'm going to describe as computing a coefficient of certain monomial in a certain complicated polynomial. So here I'm going to use a slightly unusual notation for partitions. Usually partitions involve positive integers. I'm going to pad up my partitions by adding a bunch of zeros at the end. So so even though lambda is a partition of n, it'll end in a string of zeros, and lambda n will usually be 0. So then chi lambda of mu is given as the coefficient of this monomial in this polynomial, symmetric polynomial of these x1 to xn. So this delta is the discriminant, the product of xi minus xj over all I less than j. And then these p mu's are power sums in the xi's. So it's a product over all so the partition mu also I write as mu1 plus mu2 up to mu n, again padding up with a bunch of zeros at the end. So it's a product of all these power sums, with the convention that at 0 I make this guy just be 1, and then at k it's the sum of the kth powers for any k at least 1. So I have some complicated polynomial here, and I compute its coefficient at this monomial, and that answer gives me the character value that I want, chi lambda of mu. Okay. Now this expression is convenient for congruences mod p by a simple lemma. So suppose I give you a prime p, and I give you a partition mu of n, and then I form a new partition as follows. Suppose in the partition mu, I had p parts that were all the same, m plus m p times. Then I replace, I take away those p parts and replace it by one part of size pm. Okay, so that's my way of going from lambda to mu to nu. Sorry, mu to nu. If I do that, then I claim that there's a congruence. Chi lambda of mu is the same as chi lambda of nu mod p. And the proof of this is not very hard. We just look at the Frobenius formula, which is computing certain polynomials. And we just look at the difference between the two polynomials that you have for mu and nu. So for mu, I would have had the power sum x1 to the m up to xn to the m. And this would appear p times. So it would appear like so. And for nu, I would have the power sum mp x1 to the mp all the way up to xn to the mp. And it would appear once. I've taken p parts of size m and replace it by one part of size pm. But if you expand this guy out by the multinomial theorem, then you get a congruence that this is the same as the power sum x1 to the mp all the way up to xn to the mp mod p, because all the cross terms will all be multiples of p. Okay. So that proves the lemma, and this gives you now for the first time a way of attacking the character values modulo p rather than just understanding whether they are 0 or not. So the idea is to use this lemma over and over again. By the way, I should also point out that here we are using the p is really a prime, so this part of the argument will not work for prime powers. It's restricted just to primes and not prime powers. So let's imagine the following process. I start with a partition mu. Every time I see p parts of the same size, I replace it by one part of size pm. And I keep iterating this procedure over and over again until I finally arrive at a partition mu tilde, which will now have the property that no part in mu tilde can appear p or more times. Because if there was a part that appeared p or more times, I could combine it all together and replace it by a larger part, which is p times that part. So if I go from mu to mu tilde, I still have a congruence that for every partition lambda, the character value at mu is congruent to the character value at mu tilde mod p. And now I can try to combine this idea with the Murugannakayama rule. I could try to say that if this value happens to be 0, then the value chi lambda of mu is 0 mod p. And this way, I hope to produce many more values of characters that are multiples of p. So the hope is that even though mu does not typically have a part which is as large as this, maybe mu tilde typically has a largest part which is bigger than the threshold that I need to ensure that most parts lambda are going to be t-cores. Okay, so if mu tilde has a part which is larger than this, then most lambda are going to be t-cores for that largest part. And by Murugannakayama, these values would be 0, and therefore these character values would be multiples of p. So that's the main technical result that we prove in our paper, that if you take any part p, any prime p, which is no more than log n over log n squared, you could go up to log n over log n, and that would be kind of the limit of our method. And then if you follow this process of starting with mu and then replacing it by a partition mu tilde, like we saw before, then the largest part of mu tilde for a random partition mu, the largest part of mu tilde will be, this is what you get in the Erdős-Lehner theorem, and you get to beat what you get in the Erdős-Lehner theorem by a constant bigger than 1, which gets progressively smaller as p gets larger, by an amount 1 plus 1 over 5p. And this happens for almost all partitions mu. So for the vast majority of the partitions, you will get a largest part for mu tilde, which is substantially larger than what you get by Erdős-Lehner. And then most partitions lambda will be t-cores for this largest part of mu tilde. So if you combine then this main technical result with our knowledge of t-cores, then you would get a proof of the main theorem. So let me now try to explain why you might believe this, and then give some idea of the proof. But the proof is not long, but it's a little bit technical. So the paper is not very long in general. So I will just refer you to the paper, which is on the archive for the proof. But let me just give you at least a heuristic for why you might expect this strategy to succeed. suppose you just consider partitions of n where each part appears fewer than k times. So every part appears at most k minus 1 times. So Erdős-Lehner does not make any restrictions on how many times a part can appear, and then it tells you what the size of the largest part is. But suppose I constrain that the number of that a part cannot appear k times or more, and then I ask you, what is the largest part going to be for such a partition? You might, of course, expect that the largest part should be now bigger because the small parts are not allowed to appear as too many times. So the generating function for this is just so this is the number of times the part n appears, 0 times, 1 times, all the way up to k minus 1 times. So it's that product over all natural numbers n, which is related to the formula for unrestricted partitions, which would not have this in the numerator. So it's basically the unrestricted partitions modified by a similar product. Now you can carry out the same analog of Hardy and Ramanujan. You can find the asymptotics for the number of partitions pkn, and then you could also do the analog of the Erdős-Lehner conjecture, Erdős-Lehner theorem, and then also understand for these restricted partitions what the size of the largest part should be. So if you carry that out, it's a pretty easy calculation. It tells you that the Hardy-Ramanujan asymptotic formula, you should integrate on a circle of this new radius. So it's a little bit closer to 1 than in the Hardy-Ramanujan case. And correspondingly, the size of the number of partitions, well, of course, we place a restriction on what partitions are allowed. It's going to be smaller than the Hardy-Ramanujan asymptotic formula, which is on this scale, by an amount which gets closer and closer to 1 as k gets to infinity. Okay. And now if you carry out the Erdős-Lehner calculation that I kind of gave a quick sketch of before, then you find that the largest part of these restricted partitions gets to be bigger than what you get in the Erdős-Lehner conjecture by the reciprocal of this amount. So it's a little bit larger than what you expect. So this is now a number that's bigger than 1. And so once again, we should be beating the threshold beyond which most parts are going to be t-coarse if t is the largest part, if it's a number larger than this. So that's the heuristic idea of why you should succeed. So in our case, k would be something like p. And then you're saying, what I'm saying here is that you should get an answer which is bigger than the Erdős-Lehner thing by something like 1 plus 1 over 2p. And what I showed you before was something like 1 plus 1 over 5p, which is roughly in the same ballpark. Now, this is not a proof. And the reason it's not a proof is because the heuristic is not exactly accurate, because what we have is that we have a way of looking at all unrestricted partitions of n. And we have this procedure which takes a random partition of n and then produces a partition mu tilde, which is a partition where no part appears p times or more. Okay, so what is random is mu. And what I gave you as the heuristic is if you pick a mu tilde at random. Okay, now you don't know that if you start with random partitions of mu, it could be that maybe they project down to some parts mu tilde, and maybe what it's picking out in mu tilde is not really a random partition where each part appears no more than p times. Okay, so but still, what we want to prove in this technical result is that the heuristic is more or less right, even though it's not rigorous. We want to just find some way in which we can prove pretty much a similar result carefully. So let me tell you a little bit more about what this process is, and give you a very, without calculations, a very quick idea of how the proof would go. So what is involved in this procedure imagine that you pick a number k that's co-prime to p, and look at all the parts in mu that are of the form k or k times p or k times p squared or k times p cubed and so on. So these are the parts which I'm going to combine together. So if I get p copies of k, then I will replace it by one part of size pk. And then if I get p copies of kp to the 6, I would replace it by one copy of kp to the 7 and so on. So if I imagine, if I look at all the parts of this form kp to the j, and I carry out this procedure, suppose all of these parts in mu sum to k times L. So I'm combining some of these parts and replacing them by parts of the form kp to the to higher powers maybe, and in mu tilde. In mu tilde, the same parts that appear of the form kp to the j, they will sum to the same number kp to the L, k to kl. And in mu tilde, it's easy to understand how these parts must come from, because you must write L as a sum of, in terms of powers of p, and you are not allowed to use a power of p, p times or more. So in other words, all you're doing is writing L in base p, and the base p expansion of L tells you what KL looks like in mu tilde. Okay. Conversely, if I give you a partition mu tilde, and if I tell you what the parts that are of the form kp to the j sum to in mu tilde, I can ask how many partitions mu does this come from? And again, we can calculate this. You just take this KL, so you take L, and you look at all the possible ways in which you can partition L into powers of P, and then all those ways of partitioning L into powers of P, those give you possibilities for mu that are going to push down to this particular configuration of parts of the form Kp to the J in mu tilde. Okay, so that's the a sketch of what this process is of going from mu to mu tilde. And I can describe that for you in terms of generating functions. So suppose I put p tilde of j is the number of partitions of j into powers of p. Then in terms of generating functions, so if I look at numbers of the form k times j, so this j in mu tilde, this j would be, you would write down the base p expansion of j, and then that will tell you how mu tilde looks like. And then in mu, you'd be counting that j with weight, the number of ways of partitioning j into powers of p. And that just has a generating function identity like so. It's just, this would be all unrestricted partitions of the form k, kp, kp squared, kp cubed, and so on. Okay. So in other words, on the level of mu tilde, I would have a product over all numbers k that are co-prime to p. And then these weights are what's keeping track of. So without the weight, if this were just one, this would just be some generating function for all these partitions that I'm counting in mu tilde. And then with the weights, it'll give me the partitions that I'm counting in mu, the way they're getting pushed forward into this by this procedure to the partition mu tilde. Okay. Now, if I want, so in the process that I have of going from mu to mu tilde, if this j happens to be larger than p to the r or more, then when I write any number which is bigger than equal to p to the r in its base p expansion, at least one of its base p digits must be bigger than p to the r. And therefore, mu tilde will have a part which is larger than k times p to the r. Okay, so if I told you that mu tilde has all parts that are smaller than k times p to the r, then the restricted generating function for those partitions mu would not have this summed over all values of j, but it would have it only over values of j summed up to p to the r minus 1. So in other words, what I'm saying is that if K is a set of integers co-prime to P, and I ask you to count all the partitions of N for which the corresponding partition mu tilde has largest part of size kp to the j, always smaller than k times p to the r for every k in the set, the generating function for that count of partitions for all the k not in the set k, it would just be the full generating function. This would be like unrestricted partitions. And for the elements in K, I would take the sum going only up to P to the R, up to P to the R minus 1. And then this would be something which in analytic number theory would be known as Rankin's trick, or in probability people have would call it something like Bernstein's trick. I can get an upper bound for the number of partitions of this type simply by looking at this generating function, multiplying it by q to the minus n. So, and all the terms in the generating function are going to be positive. And then if I optimize this, minimize this over all q in 0 to 1, that would give me an upper bound for the number of partitions that I need. Okay. And this is the calculation that we now perform with choosing K to be a set of numbers all larger than this threshold, which is, you should think of as being something like the Erdős-Lehner threshold, but divided by this P to the R. And then R to be something small like log n divided by P. So basically what I'm saying is that we are following this procedure of going from mu to mu tilde, and we want to know that mu tilde has a large part. What we are looking at is that we are looking already at numbers K that are reasonably large, almost on the scale of square root of 6n. Then for numbers on the scale of square root of n, we look at all the parts of the form k, kp, kp squared, and kp cubed, and so on, and combine those parts, and only look at those guys that are where k is already larger than root n. And that is kind of enough. That actually is more or less kind of optimal as well. That process produces a large value, a largest part, which is a little bit larger than the threshold that you need in order to get t-cores, and that makes the proof work. So this last part is a bit technical, and you have to go through the calculations to see what exactly is going on. But the proof is not very long; it's only 3-4 pages, and I hope that I've given you some idea of why this result is true. Thank you very much.
Thank you, Professor Soundararajan. We'll move over to some questions, maybe from the audience first. Yeah, Krishna has a question.
So,
can I ask you a question, Sound?
Sure, yeah.
You know, to construct some zeros in the character table, one stupid idea would be that use just the sure orthogonality.
Okay.
So what it says is that if you fix a character chi, then sure orthogonality says that mod chi g square, if you add it up over all the elements in the group, then it's the order of the group.
Mm-hmm.
And here all the numbers are integers. So all the numbers are either 0 or more than or equal to 1.
Right, yeah.
So therefore, since we know that chi of identity is the dimension of the representation, you get square of the dimension as one term.
Right.
And therefore, you get many terms which must be 0.
Do you have an idea of how many you would get in this way? Because
so, you know, I mean, as I said, if the dimension of the representation is, let's say, 10, so instead of 1, it is giving you 100.
Right.
So it will say that at least 99 terms will be 0.
Okay, but again, are you evaluating at so there's a difference between evaluating on the group and evaluating on the conjugacy classes, right?
Yes. So indeed.
So there are very many elements of the group on which you have the character value being 0, but it's not clear that you have many on the conjugacy classes.
Yes, so no, this will be a problem, but okay, so this is one way of creating zeros. There is another way of creating, so the orthogonality relation in the character table is orthogonality both for rows and also for the columns.
Right, yeah.
And, one can use the orthogonality in the other direction also. And just to illustrate that, if you take a conjugacy class which has a large very small centralizer. Like you said in SN, you look at the n cycle.
Yeah, okay.
So that n cycle has a very small centralizer, just n.
Right.
And then orthogonality relations say that on this cycle, all but n characters are 0.
Right. So again, so if you can again think of that, if you take an n cycle, right? Again, Murugannakayama will tell you something very strong about that too, right? Because for an n cycle, most of the characters chi lambda will not have a hook length of size n.
Right. Okay.
So again, from the point of view of picking a random conjugacy class, n cycles are also very special.
Right. No, but I think that this heuristic somehow is simple-minded, but it automatically implies many zeros.
Right. So I think this idea of looking at the centralizer also, for example, this paper of Gluck, I think follows that through, rather than thinking of it from Murugannakayama. But I don't believe you get very many. One can prove very many zeros in this way if you pick a random conjugacy class. I think. I think
Miller's theorem.
Sorry.
You said there was this difference between element of the group versus conjugacy class, and Miller's theorem was looking at the group element and not the conjugacy class.
That's right. Right.
And okay, so maybe there is some way to reach him.
Yeah, I think Miller's theorem is reasonably straightforward to see. I think probably what you're saying will also work for Miller's theorem, but also Murugannakayama immediately shows you why Miller's theorem is true. Because if you pick these random elements, they will tend to have a very small centralizer, or not of the group. Then they will be like an n cycle list happens.
Right.
1/n proportion of the group, right? So most elements in the group will have a very large cycle. So and then you can use that to prove a lot. But the structure of a random conjugacy class is very different from the structure of a random element of the group. Now, of course, yeah. So that's
Thanks. Thank you.
But I haven't, I should also look at that idea of whether it creates more than constant over log n zeros for these conjugacy classes, and I don't quite know. I think that's the best result that I know for the number of actual zeros in the character table. Might be worth exploring in connection with this. Yeah.
Are there any questions?
Can I ask a question? Yes, thanks, Sound, for a nice talk. I had a sort of as an outsider, sort of a very general question. What do you think of the possibility that for certain things, the limit n goes to infinity may not be uniform in the sense, for instance, for the zeros that you said you just failed, could it be that the divisibility properties of n itself play a role that, or even maybe there are stronger results. For instance, the divisibility by prime powers of 2 has to do with n. If you go in subsequences to infinity, where n has either even or powers of 2, and so on.
To be honest, I mean, I don't quite know how, of course, it's an intriguing possibility, right? And it could be, and we don't know how to rule it out. Somehow I would be a bit surprised if that were the case, because, well, okay, I can't tell you why I would be surprised, but I guess I would be surprised if it were the case. My kind of naive way of thinking about the zeros would be that that maybe this, and I have no basis for this either, but that maybe this 1 over log n might be the right answer. So maybe it's not a proportion of zeros. And just a very naive idea would be that you might start to get more and more terms in Murugannakayama as in this recursion. And then if you have a bunch of numbers and they're not guaranteed to be 0, and maybe some of them are positive, some of them are negative, they may not, there's no reason why they have to sum up to 0. And so the fact that they should sum up to 0 must be somehow rare, and maybe that's what happens. But I have really no basis.
Yeah, for zeros, I would tend to also sort of, I mean, just vague intuition that it probably shouldn't depend on n, but perhaps the prime powers.
Prime power divisibility, I have no idea. And there have been a few special cases that people have considered, which is things like you take one particular partition, a fixed partition of a fixed number, and then you kind of subdivide it into d by d parts, and then take a larger partition, and then those tend to have divisibility by things like d factorial. So those are the only cases where, for combinatorial reasons, you can get higher power divisibility. But those, of course, are very special, and they actually go in the line that you're suggesting, because the partition itself will have number of parts, which will be d times some fixed number, right? So, okay. So the results that I know for higher power divisibility are along the lines that you suggest, but whether that's a real, limitation or not, I don't know.
Mm-hmm. And just a final sort of question: is the determinant of this matrix, is that something? Does that have some nice properties? And especially, I mean, for instance, does that have a nice divisibility? You would, as n goes to infinity, you might think naively, you might think that it has all these powers of p you can take outside, but then it's only of order 1, so you don't know really. And I mean,
I have no idea. It's a great question. I have no idea. Yeah.
Okay, thanks.
May I ask a question?
Questions within Zoom?
Hello, may I ask a question?
Yeah.
Yeah, go ahead.
So you started by considering uniform measure on lambda and mu, and then you also considered this other measure on mu coming from proportional to the size of the conjugacy class. Mm-hmm. The analogous thing on the other side would be to consider the Plancherel measure on lambda. Would it make things different?
Yeah, so I don't quite know what one would get by the Plancherel measure. I think that's a natural question too. I think that from what I was describing, that what you would need to understand, and I don't know if anybody has studied it already, maybe it exists in the literature, I'm not so familiar with it. The idea would be to understand, if you look at T-core partitions weighted by the Plancherel measure, at what stage can you guarantee that you get measure 1? How large does T have to be? I guess if one could answer that question, you would have a similar answer based on what we have. I haven't really thought about that particular question, and I don't know what the answer is.
Okay, thank you.
It's a natural question. Yeah.
If there are no more questions in Zoom, there is one question from the audience here.
Oh, sir, do we know anything about the divisibility of non-zero character values? Because all the results that you said, so the the number of character values chi lambda of mu which are divisible by p, that will go to 1, right? So, but if your chi lambda of mu is equal to 0, then obviously it is divisible by any primes, right? So if we restrict them to be non-zero, like say let's call it actually divisible by p, then do we know any results in that restricted set? Does it also go to some limit or?
So I guess it depends just on knowing how many values are non-zero, right? Because if you know that almost all the values are multiples of p, so among all the values that are non-zero, almost all of them are going to be multiples of p for the non-zero values that are multiples of p that you like. But I don't know how many zeros there are, right? And so the question that you're asking, I think, is equivalent to asking how many zeros are there, and that at the moment we don't know.
Okay, sir. So one small question is that, does this in some way tie up to the congruences in the case of partitions, like the famous Ramanujan congruences or something like that?
Not that I know of. I don't see. Yeah, also one way in which this is different from the famous Ramanujan congruences, for example, is that this is a statistical study, right? I mean, we are not a lot of combinatorial things to do with character values or with partitions. They would say that for things of a certain type, you have certain divisibility, like p of phi n plus 4 is multiple of 5, right? Okay, yeah. So that's a Ramanujan congruence for 5. But here we are not saying something like this. We are just saying something statistical. So in that sense, I don't see them as being connected.
Okay, thank you.
There is one more question here.
Well, as in partition of Sn, we can get information about their conjugation classes. From this why we are calculating this character value means is there any relation of the property of Sn with this character value?
I'm not sure I fully understand your question, but I think, okay, so I don't know if you're asking what is the motivation for considering this question. Frankly, I have to say I don't quite know. It seems like the characters of the symmetric table seem to be a classical object, which a lot of people have studied. And somehow it was surprising to me that questions on divisibility of these had been not studied for so long, or only, or even this empirical fact is only recently noticed. And also, if you look at small tables, you don't actually see it. It's not like a numerical fact that immediately occurs to you when you look at the character table for S5 or S6, say. So, but in a different direction, your question is, maybe I could say, have people thought about questions like this for other groups or other simple groups? And I think people have been studying values that are 0 for these character values in groups of Lie type, and there's work by Larson and Miller on problems of that type as well. And again, I'm not a person who does real representation theory, so I don't know the significance of this in the study of these groups, but people have been studying these in other contexts as well.
One final round, maybe through the questions in YouTube. Srijit, are there any questions in the chat section of YouTube?
Yes, sir, there is a question.
Yeah.
So the question is, in the numerical evidence of chi lambda of mu being even in second slide, we have calculated the value for n equal to 76 and 38. Both the numbers are a multiple of 19. Is there something special about 19?
No. So I just gave you the 76 is the largest number for which Miller had his data. So I gave you the evidence for that. And then I think 38 is the largest number for which he had data on divisibility by 4, 9, 5, etc. So I just picked the largest values for which he had accumulated the data. But if you look at his paper, which is in the Journal of Combinatorial Theory from 2019, then you will find a kind of data on all n up to 38, divisibility by all these primes. And then for zeros, maybe for all n going up to 76, something like that. For not even going up to 76.
Okay, any more questions there?
No more questions, sir.
Yeah, thank you so much. So let's thank Professor Soundararajan for this excellent talk. We hope that he will come to KSOM once things normalize. Thank you, Professor.
Pleasure, yeah.